depending on which part of the world you are. Let me introduce the seminar series and its objectives. Critical Time Sessions and Complex System seminar series is being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research, PIC, in Germany. The seminar series brings together experts from the fields such as climate science, ecology, neuroscience, fluid mechanics, etc., and of course physics, and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. This webinar series takes place every month, and usually it's on the last Monday of the month, so please mark your calendars. And before I introduce the speaker, a few housekeeping items. I request everyone to keep their microphones in mute, and please use the Q&A box in Zoom to ask the speaker your questions. We have kept ample time at the end to discuss your questions and clarifications. With this, let me introduce the speaker. Professor Dibagar Ghosh is a professor in Physics and Applied Mathematics Unit at the Indian Statistical Institute in Calcutta. He received his PhD degree in nonlinear dynamics from Jadavpur University in Calcutta in India in 2009. His research spans synchronization and statistical inference with a focus on nonlinear dynamical systems and complex systems and complex networks. His current research interests also include extreme events, swarming, eco-evolutionary dynamics, higher order interactions, and climate data. He has published more than 250 research papers in reputed top international journals. And today, Professor Ghosh will speak about coexisting dynamics of swarming and synchrony in complex system. With this, I hand over the floor to Professor Ghosh.
Yes. Thank you, Professor Sujit, for your nice introduction. And I am also happy to be a part of this webinar that are organized by you in last few years. Okay.
Yeah, the slides are coming well. You can go ahead.
Coming well, but this is not moving.
Looking good.
Oh, the title is visible or?
Yeah, perfectly visible. It looks really good.
Thank you. The title of today's presentation is Coexisting Dynamics of Swarming and Synchrony in Complex Systems. This swarming and synchrony, these two self-organization in the complex systems, coupled complex systems. And today we'll discuss some models, mathematical models and their collective behaviors, where these two phenomena, swarming and synchrony, both will coexist. I just give you one just video. From there you can get some idea what is meaning by synchronization, what is meaning by swarming. In synchronization, usually we refer to the collective behavior in the complex systems by adjustment of internal dynamics, and it ignore the position or motion of the agents or of the particles. A counterintuitive, just opposite phenomena is swarming. Swarming usually referred to how animals move, and they at the same time we neglect the dynamics of their internal states. There are few examples of synchronization, just raising hands in the auditorium and fireplace, and different examples are also included in biology, physics, chemistry. In swarming, there are many examples how the animal moves in flocking birds, school of fish, or group of sheep, and ant colony. There are different examples are there where swarming phenomena can be observed. The synchronization phenomena is observed in 1967 by Winfrey. He proposed just one couple oscillators for the circadian rhythm that spontaneously synchronize. After that, in 1975, Kuramoto simplified the Winfrey model and solved it exactly. And he proposed this simple model: theta dot equal to omega internal frequency, k is the coupling strength by n-1, and the coupling between the oscillators are in sinusoidal sine of theta j minus theta I. And here n is the number of particles or number of oscillators present in the coupling. After KTL value of k, all the oscillators started from defined initial condition. They are synchronized and with time. So this is the phase synchronization among the oscillator theta I, and this model Kuramoto solved exactly that. Means the critical value of coupling after which the synchronization is occurred can be observed analytically. After a long gap in 1990, Pecora and Carroll, they extend the concept of synchronization from phase oscillator to any chaotic oscillators. And after that, 1998, they also proposed the stability analysis for this coupled synchronization using master stability function approach. I just briefly introduced what is meant by chaos and chaos synchronization. These are couple nonlinear oscillators. This oscillator is famous oscillator in Lorentz oscillators, x dot, y dot, z dot, and there are two nonlinear terms, xz and xy. There are three parameters, sigma r b. If we change the parameter I, then we can observe that the system stability, stable fixed point becomes unstable. And finally, we got one interesting phenomena. The solution is aperiodic with time, and also the solution is highly sensitive dependent on initial condition, and also the solution is bounded. So in any determinate system and nonlinear dynamic systems, these the phenomena you observe, then we can call the system is in chaotic. There are certain measurement to whether system is chaos or not. That on I go in this talk, but initial condition dependent bands means if we take two initial condition just nearby slight change, that is the same Lorentz systems, and we have taken two initial condition x naught, y naught, z naught represented by blue lines, and x naught, y naught, z naught by red lines. Their y naught and z naught are same, just part of slide the initial condition of x. Then we can see initially the system state variables are almost same. After that they are deviate from one each other. Still the phase space shows that the solution is still bounded. So from that picture we can get an idea. If the system is chaotic and two identical oscillators and they are not coupled to each other, they will not never synchronize. That two oscillator couple oscillator we call, one is sender, another is receiver. They are not coupled to each other. Their synchronization manifold are not synchronized. But if we introduce coupling, the coupling in terms of two different forms, unidirectional and bidirectional. So in unidirectional coupling, the sender sends a signal to the receiver, and we write the sender equation as it is, and response systems we added one term epsilon into x1 minus x2. By this coupling state epsilon, if we increase the coupling, then you can see the lower figure, the difference between x1 and x2, their time average decreases and tends to 0 after a critical value of epsilon. At the time series are overlapping, and also the synchronization manifold that follow x equal to y line, that is x1 equal to x1. So if two oscillators are coupled by this unidirectional coupling, so after depending on the critical value of epsilon, there is a chance to synchronize among these two oscillators. But the coupling may be bidirectional, that is two systems are send the signal to each other. That means two oscillators are talking to each other. For in that case, we also include one term epsilon into x2 minus x1 in the system 1 or sender equations. Then epsilon is the coupling strength. Then if we change the coupling strength, the system is synchronized more earlier than the unidirectional coupling. So if two systems are send their signal mutually, the system is slightly enhancing their synchrony. That is, we require lower value of epsilon. But this is the concept of chaos synchronization between two oscillators. But this concept can be extended to n number of oscillators. Then you have to use complex network theory. The complex network is represented by a graph G, and G is a set of V and E. So V is the set of nodes and E is the set of edges. So these edges the connection between the nodes can be undirected or directed, but whatever be the direction, the whole topology, how the networks form, how the different nodes are connected each other, can be repeated by the adjacent matrix A. So the elements of the adjacent matrix Aij equal to 1 if I and J nodes are connected. They are connected link, and otherwise it is 0. And AI equal to 0 for if there is no self loop. For simple graph, it is 0. Depending on the degree of this network, we can divide the network into two parts. One is homogeneous degree, another is heterogeneous degree. Homogeneous degree means all the nodes are degree are same. The number of oscillators are connected to other nodes are same, maybe local, non-local, or global network. But heterogeneous network is more important because the degree are not same. For real life application, most of the networks are heterogeneous. This network connectivity may be static or may be time varying. But if we represent any natural or neural network or any type of network, then we can see the network connectivity is not static always. It varies with respect to time. So time varying network can be represented by a graph. That graph with depends especially on time t. So gt that depends on v of t, e of t. And but for the calculation purpose or for easy purpose, we assume the number of nodes are constant and we just vary the t. Here for this, the static nodes, that means the node position are static, the connection between them are vary with respect to time. And another possibility that if the nodes are physically moving in space, due to their mobility, the connection between the nodes are vary with respect to time. So left hand figure, it shows the agents or particle are moving. Right hand side is the connectivity among the agents. The another synchronization in mobile oscillators, that is also introduced few years ago. This concept is that all the oscillators are moving in 2D plane and 2D bounded plane, not infinite plane, and each agent move in some direction. They will see the some particles and they will interact with each other. Initially, the model was proposed for two-dimensional systems by Stefano and his group, also Puneet Parmando. And after that, we introduced the concept of mobility in three-dimensional space. Also, this mobile network synchronization also extended to multiplex network also. But all these cases, the coupling is unidirectional. That means there are two motions. One is position of the agent or particle. Another is their internal dynamics. So spatial position reflect their internal dynamics. The converse is not true here. That is, the coupling is unidirectional. So another type of self-organization occurs in complex systems, that is swarming. There is a common word that birds of a feather flock together. That means we, in a conference or in a meeting, you can see this type of picture that all the people are some cluster. Those who are interested on the same topic, they are grouping some. So this phenomenon is not observed only for human, but it is also observed in animals also. In animals, the animals try to stay and also maintain a minimum distance. This is due to their predator effect or some searching of food, easy searching of food. For this purpose, in swarming, there are two key features. One is aggregation, another is alignment. In aggregation, that means whatever be the position or direction of the movement of each agent, they form a nice pattern or nice cluster. In alignment, whatever be their spatial position, their movement direction are same. In 1995, Thomas Bissek proposed one simple model for this alignment. He proposed just the dynamics in by two simple equations. xi t plus 1 equal to xi t plus velocity into delta t. And their direction of movement angle theta t plus 1 equal to theta t average over r and delta theta. This theta delta t is the average direction of velocity of the particle. That is, if a particle is here, this particle will create a vision range of radius r, and this particle will follow the next direction of movement by their average of their angles. And delta theta is the random number chosen from some uniform probability minus eta to eta. This delta t looks like a temperature fluctuation in active system. But after proposing this model, the biologists, they use the aggregation model by writing the simple equation, that is xi dot equal to vi. Xi is the position of the particle in 1D, 2D or 3D, and vi is their velocity, and their interaction contain two terms. One is the eye attractions and eye repulsion. Eye attraction means if that particle are go further away from each other, they will attract each other. And repulsion, when the two particles are come close to each other, they will repulse to each other. So inherently this equation contain two terms, one is attraction and repulsion. Using the attraction and repulsion, the agents always try to stay in a common region or in a finite region. The beauty of this model is here the bounded condition is not imposed here. It is infinite plane, the particle, but still their attraction and repulsion coupling, the particle will stay and try to stay on a closed region. The attraction and repulsion, there are different forms you can choose, but for example, if we choose the attraction is linear attraction, xj minus xi, and repulsion is Pauli type of repulsion kernel like this. But mathematically we can prove as n tends to infinity, the radius of this circular phase space of the agents, it will tend to root over b by a. But if we these three figures for different value of n means number of particle. So n equal to 100, 500 and 1000, the number of particles are expanding and it will tend to root over b by a. In our simulation here we have taken a equal to b equal to 1, so radius tends to 1 here. So this simple model is aggregation model, and the previous model proposed by Ghosh, this was alignment model. But in the last few decades, these two topics are studied independently, and there are many examples I can show you. Just the spatial and internal, these two dynamics are interconnected. How they interconnected? In this example, just synchronizing mobile oscillators, the oscillators moving in a particular direction, and in this particular direction you will create a vision range, and within the vision range those particles lie, the particle is internal dynamics is reflected by this particle. So there the coupling is unidirectional, that is spatial movement influence the synchronization, but synchronization not influence their spatial movement. But we want to propose one model that spatial movement and their internal dynamics or phase dynamics both are interaction each other. In the earlier in 2007, Tanaka and our collaborator, they proposed one chemotactic model. That model is also bidirectional coupling between spatial and their internal phase dynamics. In 2017, Stogart and his colleagues, they proposed one mathematical model that I briefly introduce what was their model. And they just interaction between spatial dynamics, that is swarming, and phase dynamics, that is synchronization. There is bidirectional coupling between these two dynamics. And they propose a hybrid model. This hybrid model give you just spatial dynamics as well as phase dynamics. And they name this hybrid model as Swarmalator, that is swarming plus oscillators. These two fields are very common because both involves large self-organized group of individuals interacting according to some rules, and both lie between the interaction between nonlinear dynamics and statistical physics, because we have borrowed some techniques from stat physics to study their collective behavior. Stogart proposed this mathematical model for this coexisting dynamics, that is the aggregation model they have taken, and Kuramoto phase oscillator they also taken. They couple this model to each other. They introduce the F attraction, that is phase dependent attraction term and phase dependent repulsion term, and also their phase dynamics reflected by their spatial position. So the two couple equation, one is for spatial position, that is phase dependent, and another is phase dynamics, that is also position dependent. They propose this simple model, and for this particular value of particular type of coupling function, I attraction, I repulsion, these two types of coupling they have taken just Paolo kernel. And also F attraction, this is A plus J cos theta J minus theta I in this form. And also their phase dependent spatial, that is G xj minus xi is also 1 by xj minus xi mod. For this model, we can mathematically prove that the particle will never interact or never collision, self-collision never occur, and also try to stay in a bounded region if their exponent alpha and beta satisfy this relation, 1 less or equal to alpha less than beta. What about their non-coexistence of finite time collision, or their what will be the minimum interparticle distance between the agents? That we can prove by these two theorems. This theorem says that if the initial data xj, x0 and theta 0, that is spatial and phase, are non-collisional, then their spatial distance, that is two particles, never interact or never collide each other, and also they maintain a minimum distance delta amount. Only the condition is the initial data that should be non-collisional. Then we can mathematically prove these two theorems. But in the model there are few parameters, that is A, J and K, and also some B parameters and alpha beta. Just we vary only two parameters, J and K. These two parameters are important. If we randomly vary these two parameters, then we found some interesting results. That is, for these three different set of parameter values, we got three static states. The first static state is each circular point is the position of the agent or particles, and the color represent the internal state 0 to 2 pi. So in the left hand side figure, all the particles are static in time and the color are same. That's why we call this state as a static synchronization state. Here the particle is static but internal state are defined by different color, that is static async state. And static phase wave state, the nearby oscillator, their phase value are same, and also they lie on a circular ring. For another set of parameter value, we also obtain active states. That means the particle are moving in 2D plane and their position are not static. And another is active phase wave and splintered phase wave. In splintered phase wave, all the population divided into some subgroup or some cluster of particles, and each cluster, their phase value are same. And in active phase wave, their neighboring oscillators phase value are same, and they are still moving on the circular way. And splintered phase wave, how many cluster will be formed and how many oscillators in each cluster, that depends on the coupling strength and also their initial condition. And if we search the whole parameter space J versus K plane, then we can see the initially for negative value of K, the system was static async state. After increasing the value of K, we got some active phase wave state where the oscillators are active. Then the oscillators are split into 2-3 more subgroups or cluster in this region, that is splintered phase wave state. And for K equal to 0 on that line, we got static phase wave states. And when K greater than 0, we just got static synchronization state. And analytically purpose, we can just derive some analytical calculation for static states. For active state, it is very difficult. For static states, we can define the density just 1 by 2 pi plus epsilon rho 1 small perturbation around this density function. Then we can substitute the continuity equations. Since the particle are static, for this purpose, we can also use this b theta omega equal to omega simply because theta value are same. If we like to, this static state all are circular way, that is static phase wave, there are two radius, internal radius or outer radius, and for static sync state only one radius. By this analytical calculation, we can derive the internal radius and outer radius of this state, and also static sync state, we can analytically derive the radius of this static synchronization state. And also static asynchronous state, we can derive their radius of the circular disc. But two active states, we cannot derive any analytical calculation. Because for static state, one of the advantages, so v equal to 0, the velocity is 0. That means in the continuity equation, we just remove one term. So rho dot equal to 0, that means rho equal to constant value. So this analytical calculation is like a low-hanging fruits that everyone is interested. But for active states, the calculation is more difficult that we are trying to do but not yet done. Then we just extend whether we can replace the phase dynamics, Kuramoto dynamics, into a amplitude equation. Because if we introduce any coupling into amplitude equation, then the field will more broader because it will open a new avenue for this research. Then we propose this model just for this amplitude equation, that is internal dynamics is xi dot equal to f of xi plus some coupling between them. And this f of xi, this is Rosler-Lorentz or any amplitude equation we can put. And we can take the spatial dynamics e to the power this form, not in the phase form. This is due to, but in some amplitude equation, the calculation of phase is slightly difficult, not always simple way we can do. That's why we use the spatial distance between the internal dynamics. That is Eij equal to the internal dynamics, their synchronization defines. So using this model, we can extend the phase dynamics into an amplitude dynamics. And we have taken the coupling between the internal dynamics through y variables. And if we fix all the parameter value, then we can get the k versus e, that is average synchronous error among the oscillators. And we also study the mean velocity. The mean velocity is basically used whether the state is static or active for this purpose. We divide the parameter space into 4 groups. In this left hand side groups, we got a asynchronous state, and also this state is active. That is the oscillators moving, and also the color are not matching or not synchronized. In the state, the synchronous error is also non-zero, also velocity is also non-zero. In the middle region, we got splintered phase wave and also phase wave states. In phase wave states, you can see just the oscillators are active states and their corresponding nearby oscillator, the internal value are same. Here internal value is the synchronization error. Also in splinter phase wave states, the oscillator is divided into more than 2 clusters, and within each cluster their synchronization error are same. And this region we got one interesting results, that is whole the population is divided into 2 parts. One part is synchronized, another part is desynchronized. That is a coexistence of synchrony and asynchrony named as chimera. And also this static sync state where synchronous error and velocity both are 0. That means static sync state we can obtain. Also some static state, that is splintered phase wave and chimera states. If we notice that one of the group are always same, another group are the synchronous error are different. So from this study we can extend the phase oscillators, replace phase oscillator by amplitude oscillators. And since we can able to do some ideal calculation for the static non-static state, that is stationary states, similar to previous case, we can also obtain for static synchronization state the radius, and also a sync state their radius we analytically calculated, and we also verify by numerical simulation by dotted line. Then there is a problem for the study of 2D model. For 2D model, it is very difficult. It is very difficult to analytically derive the calculations. After that, just in 2022, just Woon and his collaborator, they proposed one model, that is for 2-dimensional model can be converted into a 1-dimensional model. And that proposed model is just xi dot equal to this. This model is similar to Kuramoto models. Also phase and spatial dynamics are interacted with each other. And theta I dot, the interdynamics is also looks similar to Kuramoto model. And this model is very similar to this couple Kuramoto models. But one of the advantages, if we control this J and K, whatever you obtain the different states for 2-dimensional, 3-dimensional model, we can obtain by using this 1-dimensional model. That is async state, sync state, or 3-dot states are we also obtained from this model. There are different real observations of these static and unsteady states for vinegar ale or other type of solvators moving in disordered environment, where phase and spatial dynamics are interacting. And phase wave or splintered phase wave, this is also just similar examples of genus mastic or Japanese tea frogs. In Japanese tea frogs, the paddy field, all the frogs are sometimes they are lie on the boundary of the paddy field, or sometimes they make a cluster. Then after that, our main target was we can propose some solvable model of this Swarmalators in 1-dimensional, or it may be 2-dimensional model. Here the solvability means we can analytically derive the critical value of the bifaction or critical value of the stability changes where one state is transformed to another state. That critical value we can derive analytically. In 2 years ago, we proposed another model. That model is basically taken from Vizek model, but here we also impose some spatial dynamics there. That is, the spatial dynamics is xi dot equal to v cos theta sin theta, and also their internal dynamics, their spatial dynamics, theta j xj minus xi by this power law type, we have taken from the Swarmalators model. And this theta dot equal to their aij sine of theta j minus theta. This aij is the adjacency matrix of this phase value. This is spatial dependent. That means If two particle distance is less than r, the interaction is positive, that is interaction is exist, otherwise it is 0. Those special dependence, the adjacency matrix we propose here, and if we change this radius, Vision radius of each agent, then we can see that all the agents are form a single cluster and their direction of movement are same. If we decrease the value of r equal to 2.9, then two different forms, group of cluster are formed and their direction are same in each cluster and different from between the cluster. So similarly we can get a 3 cluster or 4 cluster. Similar phenomena we can see in flocking birds. Sometimes the flocks are collectively they are aggregation in a single group, 2 groups, 3 groups or multi groups. But in flocking birds, their movement are not static. They are 3 to 4 and then 1 and they are time varying. But in our model, since we study deterministic systems, there is no stochastic system we remove initially. That's where we are getting this cluster. This cluster are not matching each other. We can, if we impose any mathematical model, then the cluster may be composed and they can form looks like a V-shaped model. Then just we thought if we consider the predator and prey model using these Swarmalators, that means each particle if we consider as a prey and if we try to introduce one predator among the agent, what will happen? There are different examples. The effect of predator on the prey. The upper figure is a flock of sheep that one shepherd in the middle. The sheep is trying to avoid this man. And another one farmer is standing here. The flock of ducks, they cross the road to avoid this man. When some giant fish comes into a school of fish or group of fish, they are trying to avoid their predator effects. So from that above example, we can see the predator may be static or may move with space or time. Then we just propose one model, mathematical model, that the first model, this model has two terms. One is the spatial dynamics, xi dot, another is internal dynamics, theta I dot. In the agent dynamics, spatial dynamics, the black portion is similar to the previous model. We impose this red portion. Similarly, internal dynamics, the theta dot equal to sine theta, this term is similar to Swarmator model. We impose one term due to the predator. Here we just consider p number of predator, that the predator position and phase are like this. They lie on a circle. That is Zi is the position of the predator. Just Ri cos 2 pi I minus 1 by p and sine this term. And phase value is uniformly distributed on the circle. And we also impose the predator and prey, their attraction term, and also they are similar to their repulsion term. This term we have considered by taking inspired by the previous portion. And also their internal dynamics psi I also coupled to their internal dynamics of the predator, and they are also spatial dependent Zj minus xi within this term. Here the p number of predator like agent, they are static on a circle. What will happen? Initially we have taken the position of the box -1 to 1, -1 to 1, and the internal phase value 0 to 2 pi. And if we consider for one single predator, the equation will become very simple. These two term, extra term, and this extra term. If we put I equal to 1 in the previous equation, then this term will be R1, and this term will be 0, and this term will be also 0. But we can also shift the position of the predator at 0 position, that is by shifting R1 at 0, 0. Then for negative value of J, if we increase these two coupling, that is K1 and K2, these two K1 and K2, for positive, both are positive, both are negative, or both are 0, then we got different types of collective states. But in the previous state, all the spatial position are symmetric. But here, if you look the figure B, the symmetry is broken, because the previous figure that was symmetric in spatial and position, but this to the introduction of this predator term Z1, the symmetry is broken. For this reason, their symmetric position is also not observed in their spatial position. But in that case, we can also see the effect of J. J role is an important parameter where J greater than 0, that means those agents are, those particles are same phase, they attract each other. And J negative, that signify those particles, the phase difference of pi, antiphase, their attraction with each other. By this, we can also analytically derive their internal dynamic, internal radius, and also outer radius, Rin and Rout, analytically. For that case, since the state is static, so we have to propose some integral model, the velocity model, in this complicated form, of course. And for static states, the velocity equal to 0. And after some analytical calculation, we can derive R in, that is internal dynamics, is in terms of J, and also for outer dynamics, that is outer radius, that is also in terms of J. And also verify this with respect to J versus 2 radius. The solid line is the analytical calculation and dotted line is the numerical simulation. Still, the static state we can derive analytically. But there are some example where predator are not static, predator moving in space. What will happen? We just impose one predator dynamics, ZZ dot equal to in this form. We have taken the kernel as a power law, and also we replace their internal dynamics by a Heaviside function. This was taken because the position of prey and predator, the distance between that matter 0 or 1. For this reason, we impose Heaviside function. Then we just take number of predator as p equal to 1, 2, 3, 4, like this. But if we take p equal to 1, the bigger size green, this is a predator, and small portion, all these are prey. That is the Swarmalators agents. And each color is the internal state, that is theta I. Since we impose here the Heaviside function, so no Zi catch the prey, so they try to avoid the predator. But if we impose any random noise on the predator dynamics, then the particle or predator moves randomly on this space. This can be extended to 3-dimensional space also. But if we impose 2 predator, what will happen? The 2 predator, that means J equal to this term, and there are different forms of just pattern we can obtain. But if we notice that the predator, the prey, lie or nearest prey, their internal states are same, and those prey are distance from this predator, the internal dynamics are also different. This phenomena is similar to this above picture, that is 2 giant fish are moving onto the school of fish or group of fish. They try to avoid, the small fish try to avoid the giant fish. The take-home message is that we briefly introduce the swarming and synchrony, and these two fields are very previously these two fields are independently they have studied, not in terms of a coexisting dynamics, but after the proposed model we just extend this theory for one dimension, two dimension, and also we just give some application in preparator dynamics, and we also try to solve this Swarmalators model in one dimension, two dimension model that we can solve exactly. And also we introduce some higher order interaction in the swarming and synchrony dynamics and also preparator systems. We are working this field in 2022. After that, we have published several papers on this topic. But since this field is very emerging field and there are many applications, robotics or any animal movement application that we can present or we can propose some model for their experimental verifications. Recently, we just we have written one review article for this. This is submitted for physics report. It is extended version. Whatever theory till date, just observe. We try to review in this article. You can, if you are interested, you can follow this article, or if you have very short time and try to understand what is meant by Swarmalator, you can follow this EPL perspective. This is freely available. You can follow all this mini review also. This works done by my PhD students. Dr. Gaurav Kumar Swar is already left and he's at Canada for postdoc, and Said Anwar, he also IIT Bombay, and Somali is working with me, and Sayan Acharya is also working with me, and Somen is also doing postdoc at Italy, and also some collaborator Kevin, he's also co-author in their original paper, and Marcus from Brazil, and Timoteo Carletti is also from Belgium. This is some subset of my group in the last year. So thank you.
Thank you, Divagar, for this wonderful talk. So I request the audience to type the questions in the Q&A box. And Divagar, can you see the questions in Q&A box yourself?
No.
If you click on Q&A, you should be able to see it.
No, I can see.
Yeah, okay. So there's one question already.
So one question: as a student in the field of current pursuing control system, how to start in this field of research which colleagues are currently active in it mainly. This field is a combination of two fields. One is knowledge dynamics, another is swarming. So both are collective behavior. So I can say that you can start by getting some knowledge on basic knowledge on knowledge dynamics and also some active matter systems like swarming. Then you can combine these two fields and you can work on them.
Any of the panelists have a question at this point? Yeah, go ahead.
Yeah. Yeah, very nice talk, Divagar.
Yes,
Especially like the last part, the predator prey part. It will have applications I can see. But my question, case considers as the nodal dynamics. What happens to the dynamics once it happens? Is it going to periodic or is it remaining chaotic? Is there a change in the dynamics?
Just repeat the question. Your voice not clear.
You considered a case where you have a Rosler system or any other chaotic system.
Yes.
As the single particle dynamics. In that case, when this swarming and synchrony happens, what about its dynamics? Is it remaining chaotic or is it going?
Yes. No, it is remain chaotic.
Remaining chaotic only. There's no periodicity or amplitude death or anything like that happening. No.
The amplitude is not introduced.
Okay.
But for amplitude, we have to introduce design the coupling in different form.
Okay. And also in all cases, the spatial dynamics, you are keeping one attractive term and a repulsive term.
Yes.
Is there any other way of doing it? For example, it need not always be like that. I think you need this to confine it, no?
Now, there are other models also available in the literature.
Okay. So for example, if you have charged particles, it can be a different type.
And the different types also there. They are that means
Okay.
they are spatial. The interaction between them also spatial dependence.
Okay.
Yeah.
Okay then. Good. Yeah.
Go ahead, Professor.
Sujit. Yeah.
Yeah, go ahead.
Yes.
Yeah, Dibakar, that's a very beautiful lecture. I really enjoyed it. You have
Thank
covered
you.
so many things. Yeah. I have some doubts. I mean, clarifications I would like to need. I would like to hear from you. So what's the role of coupling, external forcing, and noise on the results you have given on Swarmalators?
In our model, just we avoid this noise term because noise term is very essential, I think, for this type of systems. But we try to avoid this noise term for our analytical purpose. Because
No,
our
but
main,
in reality, you will have to take
Yeah,
noise into
but-
account for that.
but
Yeah.
in reality, if we introduce any noise term, then whatever you obtain in static states, the static state may not occur. So in the most of the cases, it will be active states. And
Okay.
also one paper is also published by external force in the Swarmator models. In Chaos journal, there another group is already published.
So what happens when you apply external forcing? You
Whatever,
only-
this for that, if we impose any external force, within this force, the Swarmators, they are forming this nice pattern or defined groups, they form due to their external force.
Or will they get? Will the patterns get destroyed?
Yes. So some patterns are destroyed and some new pattern they observe also. This
And-
Marcus group, they publish in Chaos. Yeah.
Okay. Okay. So, okay then. We'll discuss later.
Yeah, thank you.
There's another question in this Q&A from Manoranjini.
When there is a single predator, the prey population exhibit complete asynchrony. Is this the only behavior observed? In contrast, when two predators are introduced, two distinct behavior emerges. What caused this difference? Yeah, that depends on the system, because if we introduce two predator, that means the system is, of course, is symmetry breaking. Just I can. Yeah. For this case, the for two also there is just forgot to just that the parameter value are different. Here the in the lower two figures, this parameter value is small and higher parameter value, they are almost synchrony or like two phase wave states. For different parameter value, there are different value are distinct. Yeah. I think this is the answer.
Thank you. While we wait for more questions, I have a question. Your transitions, can they be explosive and or are they continuous?
For this, those results I have discussed, all the peerage interactions, that is globally connected there.
Okay.
But if we introduce any higher interaction that we have already introduced, one is for the 1D model, another is 2D model. We have imposed the higher interaction where we obtain the explosive behavior.
Oh.
So without higher interaction, we cannot get here.
Okay, great. Thank you. Right. I think we are out of questions now. So I want to thank you for this very wonderful talk. I really enjoyed it. And also thanks for pointing out the very nice references. So we'll go through them. So we are also delighted to inform you that our upcoming webinar, next one, would feature Professor Balakumar Balachandran from Department of Mechanical Engineering in University of Maryland. Professor Balachandran will deliver a talk on November 24th on can noise be used to realize the desired dynamics. So please mark your calendars and we'll see you in November. Thank you all. Have a nice
Yeah.
rest of the day.
Yeah.
Bye-bye.
Thank you for your candidates.
Thank you.